Are you all being able to see the screen?
Yes, sir.
So today we are going to start your classical statistics or your Maxwell's Boltzmann, okay? Maxwell's Boltzmann statistics. Clear? So actually this statistics deals with your classical particle. One, it deals with what? Your classical particle. And in total, how many? There are three kind of particles. How many? Three kind of particles. Depending on your classical or quantum. How I will tell you. One is your classical and another one is your quantum. And in quantum, there are two kinds of particles. Clear? And what are the different properties for your classical particle? For a particle to be a classical or to follow your, this is followed by what your Maxwell's Boltzmann statistics. And for less for timing, just for completion, let's just write this quantum. For the quantum particle, there are what? Your bosons and fermions. Clear? And they follow Bose-Einstein statistics and they follow Fermi-Dirac statistics. Just for the completion, what we will do is we will do this part quantum particle later. Yeah. First, we will just
Yes,
move
sir.
to classical particle. So what are the properties or what are the particles which follows here Maxwell's Boltzmann statistics? Now, first is for the classical or Maxwell's Boltzmann particle, there are what? They are identical. The particles are what? Identical. But they are identical, though they are identical, they are distinguishable. Most important. They are distinguishable. And they have a spin of 0. Clear? They are spinless. Is it clear?
Yes, sir.
Is it clear? Okay. And this is for your classical statistics. And what for the quantum? For both the particles, they follow. First is these particles are identical. Identical, but they are indistinguishable. And they can have, now depending on, both have the same property, but what distinguishes between these two is they have integer multiple spin. Both have spin and this have an integer multiple spin. Just like it could be 0, 1, 2, integer multiple. For the fermions, you have what? Integer half. It will be half times n. So n will go from what? 1, 3, 5, so on and so forth. Or basically you can write this as 1, 3 by 2, 5 by 2. They have an integer half spin. Is it clear till here? Is it clear?
Yes, sir.
Okay.
Yes, sir.
So I think you all have done this, how the particles are distributed in your Maxwell-Boltzmann statistics. This is very simple. That I think you have previously done. First, I will just write the final expression. For your thermodynamic probability or your total number of microstate, have you seen this somewhere? Have you seen this somewhere? Have you seen this kind of distribution somewhere? Just
Maxwell.
do you remember when we did this kind of distribution for different cells of different sizes? Do you all remember?
Yes, sir.
This was size of this was Z1, this was Z2, so on and so forth. Do you all remember?
Yes, yes,
And
sir.
finally, we got an expression exactly this. Exactly this expression. You just go and check, but still, we'll just going to recap this. Don't worry. We got exactly this kind of distribution. And do you all remember from here what did we do? We were able to find the number of particles, if you all remember, and also we were able to find the what? And we got some expression like e to the power negative e by kt kind of. Do you all remember this kind of expression? After using
Yes,
this,
sir.
we got something like this. Okay, so let's start with this one. Let's start with your simplest example. Let's say you have two different energy state. Let's call this as E1 and E2. Clear? And you have two particles. Either you can consider this as, or you can consider as two cells. Either way, it's fine. Is this point clear?
Yes, sir.
Either you
Yes,
can
sir.
consider this as E1 and E2, or either you can consider different energy states. It's same. Clear? Now, how many different kind of arrangement can there be for the two particle to distribute? One particle can sit over here. One particle can sit over here. This is one. Another possibility is two can sit over here and two can sit over here. So how many different are there? One, two, three. Two particles we are distributing. How many times? We got three. But apart from that, what? These particles are what? Distinguishable. So if this is A, this will be B. From here, you will get into 2. From here, you will get 1. From here, you will get 1. Is this point clear? I think you have all
What, sir?
forgotten. This is AB, or either you can get BA. And there could be AB sitting over here, 0, and no particle sitting over here. And there could be AB and no particle sitting over here. Do you all remember this? So how many microstates will be there? 1, 2, 3, 4. 4 number of microstates. So exactly same thing happens for your Maxwell's Boltzmann, because the particles are identical but they are distinguishable. And any number of particle can sit in one of the state. Clear? Is this point clear? So that's why you get this kind of distribution. Now, how you can write this distribution as n factorial divided by ni factorial, and you sum this. This is your total number of distribution. You just check the previous notes, you will find that you can exactly end up with what? This kind of distribution. Clear? I think this is how we have done. Let's say this is A, B, C, and D. Let's say there are how many? 4 particles which is sitting in your this energy state. Let's call this as E1. So number of particle in your energy level E1 is how many? 4. 4 number of particles are sitting over here. The first particle is here A, can be chosen in how many ways? Now let's say you have got n number of particles. From this n number of particles, how many ways you can choose this A? Basically n number of times. In n number of ways, you can choose A. Clear? Now after choosing A, to choose B, how many ways you have? You have n minus 1 ways. I think in this manner we have continued in previous. For third one, it will be n minus 2. And for fourth, it will be n minus 3. And if you keep on continuing and do it for, and the total number of ways will be the product of this. Do you all remember or not? This is exactly how we did. Divided by what? How many ways? This is your total number of ways in which you can distribute this. But this you cannot write this as what? How many number of particles are there? 4. No, so you cannot write this as n factorial. Now, if you multiply both sides by n minus 4, then what you will get? Then you have to divide it by n minus 4. This 2 will cancel out. So you'll get n factorial divided by n minus
And
4 factorial.
4.
Yeah. But
So it's
apart from
already
that,
cancelled, no?
what?
Already got cancelled, no, sir?
I'm just adding this. I'm just adding this by hand. So that's it will be n factorial divided by n minus 4 factorial. Clear?
Yes, sir.
But apart from this, this A, B, C, D can what? They can rearrange among themselves. On how many ways they can rearrange? Basically, this is given by a 4 factorial. So to avoid overcounting, what do? Is you simply divide this by 4 factorial. And this is exactly what you used to get previously. Clear? Now that is for 4 particle. Now for different kind of particles, for let's say 3 particles, for n equal to 3, what do you do? For energy state E2, you keep on getting similar kind of thing and you keep on multiplying this. Then finally, what do you end up with? You end up with something similar to n factorial divided by n1 factorial, n2 factorial, n3 factorial, n4 factorial, so on and so forth. Clear? So that's why you got. And apart from this, now depending on your size of a cell, G1, how many number of cell can be accommodated in C1? You used to multiply Z1 into Z2 into Z3 certain way. So finally you'll end up with what? Zi to the power Ni. You just go and check your notes. So that's why you have to multiply it by Ni. Now, how do you define this in terms of energy state? Now, basically your Zi is your number of quantum states. Number of quantum states. For a given energy level, how many quantum states are there? Or basically this gives you a degeneracy. Clear? So finally, you will end up with exactly this expression, n factorial Gi to the power Ni divided by Ni factorial. This is your total number of microstate or your thermodynamic probability. Thermodynamic probability, or basically your total number of your microstates. I'm just brushing up because this we have already done in our previous lecture. So what was the condition for the most probable distribution? Condition for most probable distribution. What was the condition for the most probable distribution? Now, if the distribution is most probable, then what? It will reach maxima. So its variation or its derivative of we have done in terms of log of omega, and its derivative should vanish. This was the condition for the most probable distribution that we have done previously. Do you all remember this?
Yes, sir.
What about
Little
the
bit,
other?
sir.
Indira, Mingma, do you all remember this?
Yes, sir.
Okay. Then again, now what we have to do? We will do Maxwell's Boltzmann distribution law in general form. Now, how do we do that? The entropy, or if you take a log in both sides, or basically omega was given by what? N factorial. What does capital gamma means? It means product. It means product. divided by ni factorial. Now, if you take log on both sides, what you will get? Log of n factorial divided by ni factorial. So this you'll get what? Log omega will be, product will be what? Log of n factorial plus log of product of all these things. Now, instead of using the product, can I do, or can I write in this manner? No, from here to here, is this point clear or not? From here to here. How I'm changing this product to this summation. Should I explain this? Okay,
Yes,
basically
sir.
the product means what? Log of G1 N1 factorial into Z2 N2 divided by N2 factorial plus G3 N3 divided by N3 factorial, so on and so forth, into, sorry. Now, inside log, what you can do? You can sum all the logs. Plus log of Z2 N2 N2 factorial plus so on and so forth. So instead of using, now can I put everything in terms of summation? Log of Gi Ni divided by Ni factorial. Is this point clear now? Because this is the product, log of omega gamma Gi to the power Ni divided by Ni factorial. If I expand this, it will be this kind of this form, which will be later we can directly use as a summation. Now again, you will use what? Stalling approximation, which we have done so many times previously, because this is just a repetition for the Boltzmann law. Do you all remember the Boltzmann law? Finally, what we did before this gives paradox. So it will be n factorial plus summation over I log of Gi to the power Ni minus log of Ni factorial. I think I am able to write this division by using this subtraction. So log of n factorial will be what? Summation over I Ni log of Gi minus log of Ni factorial. Clear? Is it clear? Now later what you can use? What you can use? Stalling formula. Basically, which gives you log of n factorial will be what? N log of n minus n. So basically, you'll use this over here. So Ni log of Gi minus Ni log of Ni minus Ni. If you have any problems, just stop me in between, okay? If you have any questions. So this will be what? Ni log of Gi minus Ni log of Ni plus Ni. Is it clear till here? Now you will remember what? Now let's differentiate both sides by Ni. Clear? Differentiating both side by Ni. If you take a derivative with respect to Ni, what you will get? D of log of omega divided by D of Ni. Now this total number of particle is your constant. So what it will be? What will happen to this? This is constant, so its derivative will vanish. 0. Is this point clear? Is this point clear or not? And there is summation I is sitting over here. Derivative of ni will go, so it will be log of gi minus, now ni, you will use the product rule. This will be log of ni minus ni divided by ni, something like this. Is it fine?
Yes,
Is
sir.
it clear? So what will be the derivative of this? This will be 1. So finally what? Now for the most probable distribution, what it will be? For the most probable distribution, your left hand side, this should what? Vanish. So this should be 0. This should be 0 for most probable distribution. So you'll end up with what? Summation over I log of gi minus log of ni plus 1 plus 1. Something like this. Is it clear till here? Or any doubts? Sorry, this should be positive. Sorry. This should be positive. So this will be what? This will be negative. This two will cancel out. Yeah, this will be positive. Sorry. So finally, you'll end up with what? Summation of I log of gi by ni. Now, this should vanish. Whatever is sitting inside this should vanish. Is this point clear or not? Is this point clear, everyone? Is this point clear or not?
Yes, sir.
Okay.
Yes, sir.
Now, apart from that, what do we use? Do you all remember the Lagrangian undetermined multiplier? Previously, what we have used, because n1 plus n2 plus something summation of this should vanish, and also ni ei plus n2 e2, this also should vanish. Simultaneously, 3 equations should vanish. So that's why what we will do is we will add the Lagrangian undetermined multiply over here, because this 3 condition has to be satisfied simultaneously. Clear? Is this point clear or not?
Yes, sir.
Okay, then for this all condition 2, sorry, this is the variation of this. Because the total number is fixed, so the variation of this should vanish. So over here, variation with respect to, let's say, summation of ni, basically, it should be what? N. So variation of delta of ni should be what? Should be 0. Similarly, this also condition should be satisfied. Apart from this, and also apart from this, what do you do? This another condition. This is summation of ni ei should be 0. Clear? Sorry, the variation of delta of ni ei should vanish. So that's why what do? You multiply this with alpha, this with beta, if you all remember. So finally, what do? You add it up with this one, log of gi by ni plus alpha plus beta into ei, if you take delta ni common. Clear? Is this point clear? Is this point clear or not?
Yes, sir.
This should vanish simultaneously.
Yes, sir.
Yes,
This
sir.
3 terms should vanish. Now, if you look for the solution of ni, what you will get, or if you take in terms of negative, what you will get? if you move everything on your right hand side, or multiplying both side by negative, okay, then you'll get what? Negative negative log of ni by gi minus alpha minus beta ei should be 0. Clear? Actually, this should come with a negative sign. Let's put this as negative for time. This is just a multiplier. So let's take a negative of this one. So that's why it will be what? Negative. All the terms will be negative. Let's not multiply both sides by negative sign. So at the end of the day, the most important thing is log of ni by gi should be what? Negative alpha minus beta ei. Clear? So or ni should be what? E to the power ni by gi should be e to the power negative alpha minus beta ei. So ni should be gi times of e to the power negative alpha e to the power negative beta ei. Clear? I think this is the similar kind of expression which we have done previously in your Boltzmann distribution. Do you all remember? Distribution. This is exactly the same derivation which I am repeating. Okay, so but I am just doing it in a slightly different manner, or I am just rushing through it actually. So this is exactly what you have done previously. As you know, beta is what? 1 by kt. So the final expression or the distribution of number of particles is given by what? E to the power negative alpha e to the power negative ei by kt. So this is your final expression for your Maxwell's distribution. Clear? Clear? Is it clear? This is your distribution of number of particles for your Maxwell's Boltzmann. And do you all remember we use some partition function? Partition function z is given by summation of gi, in this case e to the power negative ei by kt. For timing, it's fine. We will continue this tomorrow or in our next lecture. But for a time being, this is your final expression, which we have done previously also. I'm just repeating it right now. So this is a distribution for your Maxwell's Boltzmann distribution law. This is how your number of particles has been distributed. And basically this Maxwell's Boltzmann law holds for your what? For your for your ideal gas and in your ordinary temperature, or in roughly room temperature. This is valid. Now, if you keep on decreasing the temperature, then what? Your quantum phenomena and different phenomena will start coming up. Clear? And the factor which is sitting over here is called what? Your Boltzmann factor. Now, do you have any problem now or any question now you can ask?
No, sir.
Any question?
No, sir.
So for the next lecture, what we are going to do is we are going to do Maxwell's Boltzmann energy distribution function. This was for a number of particles. Now we'll look into your energy distribution. So we'll stop over here.